So today we begin to explore networks composed of single elements, and what we want to learn is to see what useful concepts, what useful behavior we may derive from networks based on the simplest possible model of a single neuron. And the simplest possible model is what I referred to in my introductory presentation last week as the binary neuron, or the McCulloch-Pitts neuron. And the binary neuron has the following feature. First of all, it's a point-like element, so we ignore any anatomical structure of that thing. That neuron has an output which we denote by VI. The name of the neuron is I, and that output may be either 0 or 1. Neuron may be either active or not active. This open the lights. Okay. Okay. So that. All right. So this can be either active or inactive, and that neuron is connected to other neurons from which it gets inputs, and they are neurons J from 1 to whatever, n. From n neurons there is an input. And to this, since we want to describe dynamics, a dynamical process has to have a clock, because dynamics proceeds in time, so we have to measure time. And at the beginning, to make things very simple, we assume that time is discrete. So we have time here, and there are equal time intervals, and this will be t, and t plus delta t, or t. We shall denote it, since it's discrete, so t assumes some discrete value, so this will be t plus 1, and this will be delta t in ordinary measures of time intervals. So this neuron, now what is the way we should describe the dynamics of this neuron is to tell you how that neuron, or what determines whether that neuron at time t plus 1, whether it's active, namely in state 1, or inactive, namely in state 0, and that will depend on all the inputs. That will depend on the inputs that impinge on the neuron, on neuron I, at time t. And then this delta t is the time that the neuron uses to process the input, to analyze the input, and to make a decision. So that input we denote by U. U will be the input to neuron I. V is the output of neuron I. That input could be the current injected to neuron, if you want to relate to the actual biophysical quantities. But we here at this stage will not be very specific, certainly will not specify units in which we measure these currents or potentials, because sometimes we refer to that as presynaptic potential, the input current. So we use these words at this stage very loosely. This is the input, and that input is UI at time t depends on the activities of all the neurons connected to neuron I, sum over j, and there is a certain parameter W which tells you how neuron J affects neuron I. And these parameters are what we shall refer to as the synaptic strengths, synaptic efficacies. And these parameters can be, these Wij can be either positive or negative. In the first case, we say that that synaptic connection is excitatory. In the second case, we say that it is inhibitory. And what a signal arriving at an excitatory connection, what it does, such a signal helps the neuron to fire, to be active. The other one inhibits the neuron to be active, because now the decision is made, and VIT plus 1 will be equal to 1 if UI of t is exceeds a certain threshold. Let me denote it like that, the threshold of neuron I, and will be 0 if UI t So what we are saying is that Vi of t plus 1 Vi of t plus 1 this depends on UI of t, and if UI of t is smaller than a certain threshold here, then it is 0. And above that, this is just 1. So this, yeah.
In general, we say that each neuron can have a different threshold in this model?
I make it very general. We should not use it. Later we'll put the threshold to 0 to make it simple for all of them. But just to tell you that we are now talking about this one neuron. In principle, yes. So what you see here is this already could provide interesting behavior. McCulloch and Pitts used exactly such neurons with this kind of single neuron dynamics, now to connect them all together, to connect many such neurons. Actually, they used such neurons to produce what is called logical gates, like AND, OR, and at a later stage in our course, I should talk about gates, about logical gates. But right now, the way we should use such neurons is in a very different manner. We shall connect many such neurons, a vast number of such neurons, into networks and explore behaviors of networks when this is the dynamic that defines a single neuron. However, we want to do something more sophisticated. It's something that is more compatible with actual behavior. Because you see, the property of such a single neuron dynamic is that it is sharp and deterministic. Every input, the same input, will always provide the same output. This actually is not the case. There are a number of sources of uncertainty in the response of the neuron to the same input. For example, how does it actually happen? See, a signal arrives, an electrical signal arrives from neuron J to the certain endpoints of the axon of neuron J, and there that signal releases molecules of a neurotransmitter, molecules, chemical molecules that are released from these synaptic buttons. They float across the synaptic gap, penetrate the membrane of the postsynaptic neuron through branches of its dendritic tree, and once they accumulate there on the soma, if there is enough of them in there, excitatory or inhibitory, that is what determines the response. But you see, in this process, not every button has the same number of neurons. There is a certain distribution. Not every, the same number of transmitter molecules. Not every molecule that is released actually gets to the other end. Some of them drift away, some of them do not penetrate, and therefore there is a noise in this process of synaptic transmission. And that noise we shall now describe by a certain random parameter, because we have now randomness here, and we would like to take this randomness into account. And the way we shall do it is, you see, we assume that we have, for a given input ui, it is not this that matters, whether the neuron will fire. This is the presynaptic input. What matters if the neuron will fire is the value of ui plus a certain eta which is a random parameter. This random parameter takes into account all the sources of noise which I just mentioned, enumerated. This is what happens at the postsynaptic neuron. A presynaptic input UI generates in the postsynaptic neuron not exactly a postsynaptic potential UI or a postsynaptic current that presents UI, but something random. And it is only if this exceeds the threshold that the neuron will fire. Otherwise not. And therefore, you see that if we draw something like this, then there may be that UIT, which is lower than theta I, somewhere here, and the neuron, the postsynaptic neuron, will fire nevertheless because this, or vice versa. And now we should modify the interpretation of this diagram, because what we can talk about now is only the probability. The probability if the neuron I will fire or will be active at time t plus 1. And if I change the notation here, from now on we shall interpret the vertical axis as the probability P that Vi t plus 1 equals 1. The probability that VIT. Now, this applies also to the deterministic case, because if there is no noise, if it's deterministic, then the probability is either 0 or 1. But now we'll have something different. And it is that different that we now want to calculate. So what shall we do? We assume that this eta is a normal variable, a random variable. We have to assign its probability distribution, and the probability of eta is, we assume that this is a normal variable. Now, let me just make sure that everybody knows what I'm talking about. You expose, who has never heard about probability distributions, probability, normal distribution, normal variable? So I understand that everybody did. Well, it's already here or before, some of you before, but okay. What?
Also here.
Also here. All right, but you will not be offended if I repeat it. No? If I repeat a few things. And let me just write the expression for sorry, not at this stage. E to the minus eta minus mu squared to sigma squared. So this is the probability distribution. Mu is the mean of the distribution, and we shall assume that mu is 0, and sigma is something that very roughly, if this is eta and this is p of eta, then it looks like that. The maximum is at eta equals 0, and this is this width is roughly determined by the value of sigma, which is the spread of the distribution. The larger sigma, the bigger the uncertainty, the bigger the noise. The smaller sigma, the narrower this distribution is, and so this is it. And this thing here is here to assure that that this is truly a probability. And in order for that to be a probability, the integral of all possible answers has to be 1. So this here is to normalize. And now, yes?
So we assume that the noise here is uncorrelated. A neuron can get sick at one time and healthy at the next time?
No, we always assume the simplest assumptions that will still give something interesting. Of course, we can assume that eta is different for every neuron. We can assume all kinds of things, and then if we talk about different neurons, we can ask if the noises are correlated. No, we are talking about we still do not have a network. We are talking about a single neuron. And this single neuron, so what is now the probability that Vi at t plus 1 will be equal to 1? And that probability is
equal or bigger?
Sorry?
Equal or bigger?
No, equal. Vi is only 1. And that probability, let me denote it as follows, and we'll talk about that, is this probability will be the expectation of the expectation value of that ui plus, let me now write a few things here. Let me adopt a certain notation which will be convenient, or more convenient. Let me adopt the following notation. What determines the activity of neuron I is this difference. If this is positive, then the neuron, then this will happen. Let me just adopt a notation which we shall use, a trans hi plus eta, where hi, by hi I denote this minus this. So now let me do the following. So the probability, I'm asking what is the probability that this will be larger, that this will be positive. This will be larger than eta I, namely that this will be positive. What's the probability that this will be positive? And let me write it as follows.
Why did you add the eta?
Why did I add the eta? Because, you see, this is where I started. Here. what I said is the following. UI is the incoming signal. That UI, in the deterministic case, is exactly also the postsynaptic, what accumulated postsynaptic. I'm telling you that actually that process has noise. Therefore, UI in postsynaptic up a neuron is transformed into UI plus eta. And it is this has to be larger than the threshold.
Yes, but that's on the second half of the equation.
Okay, here?
Yeah.
All right, I define UI t minus eta. I define it, from now I shall call that hi.
So we can add
So,
the eta to the left side of the equation, and that's it.
what's the left side? No, there's no left side. I don't know. From this, I go to this, applying this notation. Okay? And now, I call this eta. Now we'll make a short calculation. You see, this thing here, this huge eta, this is a function. This is actually, this has the name, it's called a Heavyside function. And this function, I mean the property, the definition of this function is that eta of x is 1 for x positive, is 0 for x negative. That's it. That's a definition. We use this is step function. Such functions are called step functions. There is one other step function that we know that we shall use. For example, we shall use it in a few minutes. Sine of x. Sine of x is also a step function. It is equal to 1 when x is positive, equals to minus 1 when x is negative. And there are a few such step functions. So what this tells you, that this is, you get contribution to this integral only when eta is larger than minus hi. So what we now have to do is to just perform this integral and we are done. And I do it slowly because I want to show you a few things here. Yes?
What was the original motivation behind integrating the probability of theta?
The motivation, you see, if you want to know what's the probability of a certain variable, assuming certain values, you do it by summing over all possibilities. Since this is the probability distribution, we integrate. This is the probability. This thing here, or this thing here, tells you what is the probability that eta will be larger, that hi, you see, look, this is eta, and now that I'm telling you that I put here minus hi, so this integral is the probability that eta exceeds minus hi, and whenever eta exceeds minus hi, your neuron will fire. So that's what we are doing, and now we want to Yes, sure.
Don't you need to sum all the inputs to the neuron eye?
Yes.
So
You want
the
to
input is each
What?
eye, and you need to calculate all the eyes.
No, there is only one eye. There are many J's, but,
Yeah, but okay, there are many J's.
but there is only one eye now.
Okay, so where is all
After,
the inputs?
in 10 minutes, there also will be many eyes. But at this point, we have one eye. Yes. That we do not have here. In this model, we do not have spontaneous firing. In this model, everything is driven. Yeah.
Can you explain again why this is where the neuron will fire and the distribution of...
Because if because every point here, for every value of eta here, eta, for every value of eta here, this is positive. Why is that?
What's the
Why is this positive for every value of eta?
because it's smaller than... Okay.
Yeah.
Bigger than...
Yeah. If h, yeah. So let us quickly compute this, and 1/2 pi sigma squared minus hi to infinity e to the minus eta squared eta squared 2 sigma squared. Let me define a new variable z equals eta 2 sigma squared. So in terms of this new variable, what I have here is minus square root of pi minus hi over square root of 2 sigma squared to infinity e to the minus z squared dz squared. Everybody followed me? How I did that? Okay, so now let me tell you the following. Let me tell you that there exists a function which you may have encountered before or not, but I'll define it for you. A function erf, it is the error function, plays a central role in probability theory, and erf is defined erf x is defined as 2 over square root of pi from 0 to x, from 0 to x e to the minus, say, z squared dz. Now, what is this function? This function, what is erf of infinity?
2 pi over 2 square root of pi over 0.
No?
1.
1. Why 1? Because erf of infinity is, because you see, the integral over e to the minus z squared dz from minus infinity to plus infinity is square root of pi. Very good. So 1 over square root of pi is 1. So from 0 to infinity and from minus infinity to 0, yeah, it is 1/2. And Therefore, in this definition, we have a 2 here. And so if you take it from 0 to infinity, this is 1. And f of minus infinity is minus 1. I put minus infinity here. And from minus infinity to 0 is 1. From 0 to minus infinity is minus 1. So you see, and for every x, what is the error function? How is related the error function of x to the error function of minus x?
Always it's not minus.
What?
Always it's minus.
Error function.
Minus x is minus the error function.
Okay, so it's an antisymmetric function. Yeah. Antisymmetric. F of x is equal to minus f of minus x. This is the definition. Okay. So this is, so we now have this. And now so you see that this thing here, what we have here with this definition, with what we have here, I shall now write the final result and say a few words about it. If we look at this thing here, what it tells you is that this here is, which is V I, t plus 1, t plus 1, 1, t plus 1 equals 1. The probability that this actually is the case is now 1/2. You see, if I take 1/2 because there is no 2 here. In the definition there is a 2, now there is without a 2. Now this I can split up into 2 things, from 0 to infinity, which is just 1/2. And then from here to 0, which is error function of this. So I have the following plus f of h I so this is it. But now let's take another step. Now I make an approximation. I'm making an approximation. Error function came in here for obvious reasons. Always appears when we deal with normal variables. But let me tell you, you can verify it, that if you plot 2 functions, one is the error function of x, and the other one is the hyperbolic tangent of x. And if you do not sharpen your pencil, you will not, they are not the same, but you will not distinguish. Now, what is the tangent? And I prefer to see the hyperbolic tangent from this moment onwards as one of our key players. Why? I'll tell you immediately after we take a break. Today I do breaks because I have a cold and I have to rest my voice, so we'll have 2 breaks today, but we finish on time. So, but let me just tell you, so this is it. And now I am telling you that that P VI T plus 1, the probability that this equals 1 is 1/2 1 plus hyperbolic tangent of HI. Now before I divide it by this square root of 2 sigma squared, yeah, which is the measure of the noise, and we'll see immediately after that how it is demonstrated on this plot. But before I do that, I want to give this parameter 1/2 sigma squared another name. I want to call it, and this is just a name, but it is a very useful name, as you will see. This I want to define and to call it beta, or T minus 1. But T will remind us later of temperatures. But it has nothing to do with the temperature that you would measure with the thermometer. It has to do with temperature in a physical system that measures noise, uncertainty, randomness, and so on. So what we have here now is this. Beta going to infinity, now don't be confused, beta going to infinity is 0 noise. Because beta going to infinity is 0 temperature. Beta going to 0 is total uncertainty, as uncertain as it can be. So 10 minutes, okay? I'll call you in.
Arrow function והטנגנט.
כן,
אבל זה ארק טנגנט.
ארק טנגנט?
כן,
כן, גם ארק טנגנט.
איזה שליטה, זה מדהים.
איפה דנו? זה מאוד, תודה שצחקת.
מה שהוא אמר לפני שתכנס למתמטיקה, שהוא דיבר על אתה צריך לעבור על מאוד בסיסי על ביולוגיה של וויקיפדיה של ויקיפדיה של נאס"א? לא, זה ברמת ויקיפדיה. זה לא יותר מזה, מדבר על זה ממש אפילו יותר מזה, הוא תיאר את זה בצורה לא נכונה. כן, בסוף העניין של הקלקולרים. לא משנה.
יפה. משהו מוקדת?
הסתברות הזאת אני יודע, אבל נראה לי מדע כזה שיש כאן. זה גם למשל, אני לא אפריע לו אם הוא חוקר גרון לזה, אבל כל ההנחות שם לא עלינו להם כאילו זוהי ומאמין וזה כאילו. הוא הייתה לנחש, אותו שכן לא יודעת, זה לא הייתי לנחש. שהרעש של הנוירונים לא ישים את זה.
של אחר הרעש, פשוט שיש הרבה מקורות של רעש בטיפול שיוצא.
זה הגיוני, זה נשמע קשה, ההסבר הזה, זה גם נותן לך את השונים, זה גם נותן לך מיהו שונים מאפס. יש ליותר דרכים להיקשר מאשר להצליח, זה כלל יידישאי ידוע. סיבות זה פחות.
לא, כי העניין, אני רוצה יותר אפילו לרעש ברמה של באמת כאילו שכל אחד ואחד מהאינפוטים יכול להיות קצת יותר קצת פחות. נכון. זה יכול להיות יותר, יכול להיות פחות.
כן, יכול להיות שיש לו כסף בנוירון שנוירון א' משדר נוירון א' הוא בשידור יתר
פשוט כל פעם שא' יורד מה שבאמת כאילו נכנס לזה, כן,
שהנוירון בעצמי סביב לבית חדשה. מה שאתה אומר זה שיש, כיוון שיש מקורות לשני הצדדים, כיוון שיש הרבה מקורות, אז זה לא בקירוב, אבל הוא לא מופרח.
ברור כן אחד לשני. רגע. ערבים. איפה היה להם תראה מה קורה בסוריה? הם מנשק לנו את הידיים. גם אני אומר זה, אני אומר זה מזרח עות'מאני. מה אכפת?
למרות שזה מה זה משהו, זה ברור שאנשים מדברים על זה, אם יום אחד יש לי את הדעה.
זה ברור, זה ברור כמו שהוא יורה, זה ברור. כן, זה ברור. לא יכול להיות שבאמת הם מקריבים כאילו שתפסו אותם. זה ברור כי הם פוחדים, זה ברור. זה ברור? זה הצלחה מאוד מסוימת. למה? כרגע החלנו, זה 50 אנשים, ואמרנו שבעצם הוא אומר לך רק אם פחדים. לא. אבל זה ברור.
So this is the result that we just derived, and I wrote it down now explicitly, more explicitly, and you see what happens when beta goes to infinity. Beta goes to infinity means that it is a deterministic case, there is no noise, and when beta goes to infinity, this goes to 0, this, here we have 1, no, this and this goes to 0 when beta goes to infinity, and we have the following, this case. And what happens to a hyperbolic tangent itself when beta goes to infinity? It becomes, the hyperbolic tangent is an anti-symmetric function, and I just mentioned to you that this is the other step function, which we did not mention yet. When beta goes to infinity, P or Vi equals 1 is 1/2 1 plus sine of beta h, and this sine is this anti-symmetric step function, because you see it's either 1 or 0.
Do you need beta in this?
You don't need beta in this here, because beta is sorry, you don't need beta in this. This is beta goes to infinity. You don't need, thank you. This is no beta. Here. So this is it. And if you plot for any finite beta, when beta equals 0, this is 1/2, and for when beta is very large, when beta is very large, this goes to 1, and it goes like that, and if beta, except that in our, this is the previous notation, when we replace ui by hi, then just make so this here is 0, the threshold is then 0, and this is what we just derived. Yes, you're right.
I don't understand how in this count also UI.
Also UI.
Yeah, because
Now UI is is in the definition of HI. In order not to carry along this theta I, the threshold, I define now with respect to the threshold.
Yeah,
so I define the threshold of saying that the threshold is 0. Yes.
what I mean is that in this equation, when
Which,
beta goes
this one?
Yeah, when beta goes to infinity, you said it's always going to be 1, right?
Yes.
But
For sorry. If beta goes when beta goes to infinity, it will be 1 for positive h.
okay, so this is what
It will be 0 for negative h.
Okay.
That's what
That's
that's what I should have said. So that's it. And now, since we have this, we have a binary. We have a binary neuron. There are 2 states, 0 and 1. We have this kind of single neuron dynamics, which now has a noisy behavior. I'm tempted already now to tell you that this has this thermodynamic formulation of its behavior. So now I am tempted to make analysis. And remember, last week I had this PowerPoint presentation, and I mentioned to you several attempts by physicists to benefit from metaphors between this and physical two-state systems. And one physical two-state system, which is an ideal candidate for such metaphor, is the magnetic moment. So the magnetic moment, now I teach you a little bit of physics. The magnetic moment, it's like the needle of the compass. The magnetic moment in a magnetic field, which let's denote this magnetic field by H. Yeah, in this magnetic field, and there is a certain magnetic dipole, which we usually denote by mu in classical physics, and that has also a direction, and the energy of a magnetic dipole, magnetic needle, a compass needle, in the magnetic field, the energy is minus h scalar product with mu, minus h mu cosine theta, and that tells you that the lowest energy is when the magnetic needle is in the direction of the field, the highest energy when it is anti-parallel to the field, and the classical magnet can be anywhere between. But not so a quantum dipole. In quantum physics, the direction of such magnetic dipoles is quantized. In particular, there is a large class of such dipoles which have only 2 directions. These are states in physics. They are states which have spin 1/2 or minus 1/2, but that's anybody who has a physics background should know what I'm talking about. But for us, it's enough value that we assume that we have this magnetic dipole, which can be in one of 2 states, which we shall denote by S, and this S could be either +1 or -1. And +1, plus or minus, refers to the direction of that dipole with respect to the magnetic field, and there are 2 states, and so there are 2 energies. E is equal to minus H minus HS, and when S is equal to +1, then E is equal to minus H. When S is equal to -1, then E is equal to H. Yeah. See, this is like in a physical system, the lower energy is the ground state, and the lower energy, that's why we have a -1 here, if we want to define the parallel direction of the spin. We should call that a spin now. The parallel direction of the spin, of the magnetic dipole spin. I shall use these words interchangeably, but you know what I mean. And this is it. Now, so we shall draw, we should benefit from such a metaphor, and what we shall do is, well, we shall, until now, we denoted the the activity of the neuron, of our binary neuron, is 0, 1, and was by letter V, and now we shall use SI, which will be +1 and -1, and we would like to transform everything that we did until now, not much, but we did something, into this new notation, where we shall understand that this VI equals 1 should correspond to SI, and 0 to -1, and the way to do it, of course, is that if SI is equal to 2 VI minus 1, then you see when VI is 1, then SI will be 1, and when VI is 0, then SI will be -1, and this is the transformation. And what do we have to rewrite now? We have to rewrite our expression, the expression that we had before for U of I, which was the sum of J Wij V J minus theta I, that was the threshold, and I could also add, if I so wish, I could add some UI 0. That is something which I did not put, that is not mentioned before, but this, you see, the input to the neuron could be also from an external source, from an electrode, from other areas in the brain. So what you have here, this is the input to the neuron from all other neurons, and this would be some additional. And now let me write this as JWIJ Sj plus 1 divided by 2.
that equation, shouldn't it be Vj?
What?
And Vi?
Vj, certainly, yes. Set I plus ui 0. So you see, I now replace this V in the new notation, and let us now denote, and this should be a sum over J. And now let me write it in the following way: J I J S J sum over J plus a certain HI 0. Now, tell you why I am using this notation. First, this HI 0 is everything here that does not depend on J. Everything I put in there, some constant. And this thing here, this Jij would be the previous W divided by 2. That's not important. What's important is that I gradually adopt more and more of the adopted, of the common notation in physics. In physics, treatment of magnetic systems, of spin glasses, not yet, of of systems of spins, we use this parameter Jij, which denotes the interaction between dipole J and dipole I. In our case, this refers to the synaptic efficacy that we talked about before. This is the interaction. But this is our notation. Now, why do we denote it like that? Because this we shall now, this whole thing Hi is equal to whatever you have on the right hand side. And again, the letter H I'm using because physicists use letter H usually in this context to denote the magnetic field. And look what we have here. In the language of magnetic systems, this term is the magnetic field acting on dipole I due to the interaction with dipole J. The sum over all other dipoles is the magnetic field that dipole I experiences because its interaction with all other elements in the system. And then there could be, doesn't have to be, but could be in general, also a term which is independent of J, which is due to some external medium. And now, if we do that, now we shall ask the following question. Exactly in this sense, we shall ask the question, what is yes?
Could you define J and all the variables in terms of the old variables?
In terms of the old variables, Jij is just Wij divided by 2. If you look at this here,
What
yes.
happened to...
Oh, but is it, it's not a determinist, like, is it deterministic? No. We need to, if we need to calculate probability.
No, no, until now, I did not tell you anything about the transitions between different states, or what determines whether a spin or will be +1 or -1. I did not tell you yet, but I shall in a minute, and that's what I'm going to do now. I shall in a minute tell you in physics what is the probability. Now we have two states. We have one state is E plus beta H. This is, say, we have two states, E1, E2. E1 has lower energy than E2. The energy E1 is minus, I have it here, and that is E1. It is, I have to, one state is when we had it just before. I have it somewhere here, but let's do it again. So we have the following: when E equals minus beta H. E equals minus beta H. And that corresponds to S equals +1.
minus H.
What? Minus H. This correct. We still do not have beta. Minus H. And the other one is H, and this corresponds to S equals -1. Now let me tell you another result from physics. And we shall use this later. Today, next week, you can anticipate it. I will tell you under what condition what I am going to write now is correct, can be written, under what conditions it's not exactly the case. But we say that in general, here we have a system of two states, of two energies. Suppose we have, in general, when we have a system of discrete energies, E1, E2, E3, and so on, a number of such states, not just two. We should immediately specify two, reduce it to two, but we have it in general. So now I'm asking you, in physics, what the result is, that when our system is in contact with a temperature, T, and temperature T is, in our notation, what is the T? 1 over beta. Then there is a certain probability to find our system at a given energy. The probability of energy to find our system in a state of energy Ek is given by e to the minus beta Ek divided by sum over k of e to the minus beta Ek. Now, first of all, what is the meaning of this? First of all, this is the distribution that we attribute to great physicists, thinkers, who are the founders of statistical physics, Boltzmann and Gibbs. All. And the denominator, of course, we need to normalize these values, because these are probabilities. So the sum over all possibilities, the sum over all k, has to be equal to 1. And this is what is assured here. Now, what happens when beta goes to infinity? Let me show you what happens formally. Let me show you what happens. You can guess what happens when beta goes to infinity, but let me show you formally. P of ek, I can write that as E minus beta E W ek sum over all the possibilities. And let me now write all the possibilities as follows. E to the minus beta E1 1 plus E to the minus beta E2 minus E1 plus E to the minus beta E3 minus E1 and so on. You understand what I did? I just pulled out the first term. Now, all these, the E2 minus E1, they are all positive numbers, and therefore if beta goes to infinity, every term but the first vanishes. So this is not there. When beta goes to infinity, every term here, this is positive, so it vanishes. You have 1 here, and now it depends. For k, p of E1 is 1, if you put in here 1. But for k other than 1, k not 1, what is it? 0. So you see, this is obvious, you could have guessed it, but it's to be exposed to such very simple manipulations, which we should do again and again. So this is it. Now I want to take you somewhere else, yes?
When you transfer from the finite model to the physics model of people, and you change the Wij, which stood for synaptic strength, etc., what would be the equivalent in the physics world?
The equivalent in the physics world of what?
That there are certain inputs which different ways and impact and exactly.
Look, in the physics world, usually, if you have an ordered material, then the Jij's are the interactions, and there are very regular, usually they are great regularities between magnets in a crystal. But if you have, but there is a whole system of magnetic materials where these Jij's, these interactions are random, just like they are in this case. And it is from those systems that we shall derive certain lessons.
But they're not completely random in our brain.
Not completely. Nothing. not completely random, but they are random. First of all, physical, there are great difference. The greatest difference is something that we shall learn today. The greatest difference between the JIJs in a physical system and the JIJs in our system. The greatest difference is that in physics, every JIJ is equal to JJI. In physics, we have the third law of Newton. Every interaction is balanced by, and therefore, in the neural system, it is certainly not the case. What that means, what are the implications on what we are doing, we'll talk about it still today. This is the major. So this is now it. And let us now go to our two-state system. And on our two-state system, the probability of having, if we adopt this to our two-state system, then the probability of having the probability of Si equals +1, yeah, will be E and minus beta Si plus 1 will be E to the beta h, because you see you have here minus energy to the beta h, E to the beta h plus E to the minus beta h. There are only two states.
Same the big H that it was there.
My small h now is the magnetic field, the total magnetic field that my dipole experiences. So this is it.
What is the relation between the big H and E? Can you just write it down?
Yep. Si, we had the relation here. Si, okay. In order not to confuse, let me write this here. Yeah. I started, you remember, I started from the general case from physics, but let me write this down. And this I challenge you now because I want to take too long. This is equal to 1/2 hyperbolic tangent of beta h. That is something that already looks familiar. We know that this can be interpreted now in two ways, and we'll talk about that. Can be interpreted as the probability of having that spin in equilibrium. In equilibrium at temperature T, or it can be also interpreted, and now I want to say a few words about that Si T plus 1 equals 1, that is how we started, of Hi at time T. You see, this thing here, the Hi at time T depends on the entire configuration of spins. Which of the other spins are state 1, state -1, and so on. And the system now, spin I, looks at that field, and if it is parallel to that field, then it is happy and nothing happens. If it is anti-parallel to that field, it will flip the spin. So we have this expression here. And of course, once all spins are happy, then nothing changes, and this is the equilibrium relation. So we have this thing here, emulating that process, that dynamics which we described before. And now I shall ask you, what is the probability that SIT plus 1 will be -1? What is that probability? What? Will be minus. There are only two possibilities. You don't have to do any calculation. There are only two possibilities, and the sum has to be 1. And therefore, so this is it. Sorry. This. And this we can write in a very compact form as the probability of probability of SI, I'm dropping the times now because this would be interpreted either as dynamics or as an equilibrium statement. PSI equals 1/2 1 plus SI beta HI. So you see this, I've written the same in a compact form. If SI, the probability for SI to be 1, I have to put 1 here. The probability of SI to be -1, I put -1 here, and this is something compact that you should also. Now, before we break, I just want to put one expression on the whiteboard, and then we'll discuss it after the break, and that is the following. In this physical system of ours, as we know, every spin or this magnetic moment experiences a certain field, HI, and in that field, its energy, the energy of this spin I in that field is -HI SI, and this will be equal to -J I J S J times SI. You see, this is the magnetic field due to interaction of all the other spins minus HI0 SI. And now this is the energy of a single one, and what is the energy of the total system? I have to sum over I. But when I sum over I have to be very careful in physics, because then I double count, because I count everything. I could be 1 and J could be 2, J could be 2, I could be 1. Instead, in order not to double count, I have to divide this by 2, it's 1 Jij Sj Si minus Hi0 Si, sum over I. Sum over I and sum over J. And this is a function which is defined in the space of all possible configurations. And this function we refer to as energy. And in physics, this is a function which can only decrease. And it decreases until it reaches a certain minimum, usually a local minimum. And the Jij's are general. All Jij's, there is a single magnetic system, and like a ferromagnet. Then again, there are 2 minima, but in the cases that we shall discuss, there are many more. So after the break, I would like to explore with you this property. Just what I just said. That every step, remember, we have this discrete time still, and at some time we see what happens if one of the spins flips. What happens to the energy? One of the spins changes itself. And that we'll do after the break. And draw some conclusions from there, from the result, for what we are doing. Any questions before the break on that?
אני לא כל כך מבין מה הרווחנו בכלל מהמעבר לספין, בכלל מה החשיבות של ספין מתהפך או לא, איך זה, מה זה אומר?
ספין מתהפך או לא, זה אומר שנוירון שלך לא היה פעיל, מה יגרום לו להתפתח. ספין מתהפך או מים היה פעיל, מה יגרום לו להתפתח. וזה ההיפוך של ספין הוא בדיוק מייצג את אחת משתי אפשרויות. ומה הרווחנו? הרווחנו שיש כל מיני מושגים, וזה אנחנו... בשיעור הזה נתחיל, בשיעור הבא אנחנו את מלוא המכניקה הסטטיסטית נגייס לבעיה הזאת.
עכשיו, ספין זה בעצם סיבוב של האלקטרון סביב... זה לא משנה. עכשיו, מה גורם בכלל לספין להתהפך בעולם הטבעי?
לא, הזמן הם מתהפכים. קודם כל, בטמפרטורה שונה מאפס, אז יש כל הזמן פלקטואציות. וזה אם ברגע מסוים הוא רואה שהשדה המקומי שהוא מרגיש לא מגביל לו, אז הוא מתהפך. זה רוצה להיות מגביל לשדה.
קטנה חלוקול, גם בשבת בסכימה כפולה, אתה שולט את דברי ה-YII, כן? זה בכוונה או שזה לא קשור?
שמה?
קורא כאן דברי ה-II, כאילו, אם זה שתפינים עצמם.
אין לי משהו. לא, זה חשוב מאוד, אין II. אין אינטראקציה עצמית.
אז דבר שני, הוא מגיע באיזשהו פיזיקה, אני מכיר, אבל את המושגים הנוירונים
אז אנחנו כל הזמן נשחק בין שני המושגים האלה. הרי כמו שהוא שאל, מה פירוש הדבר שספין מתהפך? פירושו של דבר באיזה תנאים, ניורון שהיה פעיל בשלב הבא יהיה לו פעיל, ולהפך, זה מה שזה.
כן, אבל זו פעם ראשונה ששמעתי על זה בכלל.
בסדר.
אני התכוונתי ברמת המושגים, נגיד, קצת שהוא דיברת, אמרת את המילה דנדרית שאני שמעתי אותה פעם ראשונה.
טוב, זה לא חשוב לך כל כך. אני אמרתי, זה אנטומיה של נוירון. אצלנו נוירון הוא נקודה. אין לו דנדריטים ואין לו אקסונים ואין לו כלום. אני אמרתי, מדוע בנוירונים ביולוגיים יש רעש. יש רעש בעברה הסימטרית. וזה אנחנו מייצגים על ידי
נלמד על מבנה הנוירון שנגיד.
לא אצלי.
דבר, אין החלש לבן, שאלתי את אחד הביולוגים, פשוט, אבל חוץ מזה, חלש לבן הוא גם סימטרי. אני הייתי נושא שהייתי מניח שהמערכות יכולות להיכשל יותר...
לא, תראה מה שאני ראיתי, לא, זה בדרך כלל, הרי כל אחד מהדברים שאני הבאתי הם דווקא התפלגות שם, איפואסונים. אבל סכום של הרבה איפואסון נורמלי.
כי יש הרבה מקורות.
כן, בטח. זה אני פה.
אבל
לא תגידי שזה
לא, איך תגיע?
זה ממש מחובר.
בתור UI.
אני אומר, אני מודד H ביחד לזה.
כן, ב-H אני מבינה, אבל בתוך הגדרה של U.
אין יותר, אין יותר.
בדרך היה U.
בדרך היה U, ואת ה-U אני מודד ביחד לזה. אני מודד אותו ביחד לזה.
לא היית בעצם.
אני לא הייתי ואני גם לא הייתי.
קורא לה הפרש בין U לזה, אני קורא לו U. אני יכול להגיד, הרי תטא זה קבוע. הוא לא תלוי במרכיבים השונים. אז בסדר, אז אני יכול לבלוע. יש לי עוד אחד. אני יכול לבלוע.
אני למדתי
קבוע.
אני למדתי כביכול שם. עכשיו התחלתי שנה. בהגדרה למדתי קראש קורס ביולוגיה של נוירונים.
אז זה נראה משהו שהוא חלק כבר עשה מגן אפקטיבי.
ממש בשביל קבוע שם. כאילו...
זה קורה כאן, נכון? כאילו זה או זה נכנס
כן.
פה, או זה נכנס פה, או זה אפילו...
כן. פשוט בעצם זה עוד אחד משליטים. כאילו אני מודע משהו
מה שאני לא ראיתי, למה יש חצי פה בזה? בעיקר רוצים לדפוק עם כל אחד ואחד. אז מה הבעיה עם FJ יופיע פעמיים לפי פעם כי יש לו השפעה?
לא, גם כאן אמרתי פעמיים. כאילו אם לא יש לנו, נגיד אם לא יש לנו.
זה לא טוב. שאני לא נצטרך כל השבוע. עד שזה תקשיב, שלא לדבר כאן. אז הוא אמר שלא טוב. כאילו אותי הוא היה, איזה בא, אבל זה לא, אני כיף, זה גיבת. לא אכפתי שלא ידבר בחיים, כאילו נורון, כן, לא, אני אסתכל מה זה. כאילו, תלוי איך זה תשאל את זה, כאילו כמה...
אני חושב שאני באופן עקרוני לגמרי לא מתפססת כי אין לי שום ידע, יש לי איזה מאוד מינימלי. אני חושב שיש משהו שונה קונספטואלי, יש משהו שונה קונספטואלי, משהו לא משהו לא מספיק, לא מספיק שיכול לעשות את זה בהרבה של פרוט לסרטן, יש שם לא נכון
Alright, so we wrote this function down here, and we I told you that in a physical system this is the energy, and the property of the energy function is the following: that if we have a dynamics without noise, we already saw what dynamics without noise means. Dynamics without noise means that if at a certain time, at time t plus 1, spin, let's say spin k, we have here i's and j's, but let's choose a very specific element, a very specific neuron, which we shall not sum, k. If that spin k looks at the magnetic field that it experiences, and if the magnetic field that it experiences, hk, only then, if that magnetic field, sk, times hk, is smaller than 0, namely the spin is antiparallel to the magnetic field, at times t plus 1, that spin will go from sk to minus. Only then and only then. And the claim is, in physics, that whenever something like that happens, this function, if we compare this function at t plus 1 to this function at times et, yeah, the only difference will be the flip of spin sk, then this function has decreased. And so this function will decrease each time that such a condition will occur and will compel the spin to flip, and then the function will decrease until it can decrease no more. Then it has reached an equilibrium. And this is the essence of an energy function. So let's explore what happens to the energy functions when we take here this particular spin and we flip it. So here we'll have minus, we flip the spin. Instead of sk, we put minus sk. Yeah? And therefore, there will be a plus sign there, and there will be a sum of, say, I, let's say k, j, j, k, j, s, k, s, k, s, I. What I've done here now, I look over all the spins sk, sj. I look over the index I when I is equal to k, I change that term. Then there will be many other terms which are not changed. Then I look at index j. And at index j, I'll have plus 1/2 j sum. There's no sum over k, so let's notice that. Now we have a sum over I and j I k s s I s sk. You just make sure that sk. And then there is this term, and this will be plus hi 0, hi, not hi but sk. And then there are all the other terms, which you keep in mind that there are, where neither I nor j is equal to k, and they do not change.
In the left side, it should be the et plus 1 and minus et.
A moment. Now it's now e plus 1. Now if I write et, I just specify these terms. j, k, j, sk, sj. Here sk did not change. Here sk is the original, has its original value, therefore the minus is unchanged, and minus 1/2 sum over I j I k s I sk minus hk 0 sk, and then there are all the other terms where neither I nor j is equal to k. And now I want to calculate delta E, which is this minus this, will tell me what is the change in the energy that occurred because of this. And all the other terms are the same here and the same here, and therefore they cancel. And what I am left with is this minus this, which is sum over j, jk, j, sj, sk, plus sum over I, J I K S I S K plus 2 H K 0 S S K. Now, what do I have here? You see, the thing is that this thing here, what does it look like? This is the field, the magnetic field, the interaction of all other neurons that neuron K experiences. So this is this, so if we take this and one of these, we have here H K S K. What I have done is the following. You see, we have two terms, 2 H0SK. I take one of them, take the SK out, this plus this is SK.
You didn't write in both equations, you didn't write the constant, which is due to all of the other things, right?
I did not write it.
Yeah.
There are many, many more terms which I did not write, where I and J are different from K.
Yeah. Okay. So you write
Because they cancel out.
this is all the input that the neurons and what is
This is the input that neuron K receives, or that is the field that spin K experiences. And then we have the following. So this is fine. And then we have I, J I K, S I plus HK0 times SI. So you see, we have this first term, which we know, we interpret, yeah, S, H, 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 K, S, K, K, S, K, S, K. So then we have this first term. Now the first term, what is the sign of this term?
Smaller than 0.
Otherwise, if it were not smaller than 0, there will be no change. So this is smaller than 0. Now what is the sign of this term? The answer is, I don't know. And you don't know. Could be I. Why? Because what is here, you see this combination of J-I-K times S-K is not the field on site K. When will this term, under what condition will this term be the same as this term?
If the Jij is symmetrical,
If Jik would be equal, if I can instead of this write Jki, then you see this is also the magnetic field. Now in physics this condition is guaranteed.
What is,
Yeah.
why is it the same?
No, because you see, because what you have
I and
here,
J is
because then what you have here is the sum. What you would have here is the sum of I over I of J K I S I, and this is exactly the contribution to the field from all other neurons I that are not like K. Well, in this form, it's something very different. If JIK is different from JKI, then it is not the case. So you see the condition for this function E doing what I told you that it does is that the interactions are symmetric, as I emphasized that in the physical system they are. In the system that we are exploring, they are definitely not. Not only, you see, the synaptic connections between two neurons are not symmetric. They proceed through different channels. It's not the same channel because the interaction is not such a force at a distance. It is an influence through transmitting certain molecules, and and these channels are unidirectional. Also, in many cases, if neuron I is connected to neuron J will not be connected to neuron I. So you see that we have a therefore, if we take that seriously, and if we are at this stage discouraged by this, then we have to give up this approach, but we will not. We will assume in our models for the beginning, again, we ignore that difficulty. And let's assume that everything is symmetric and we have this kind of energy. We later relax that condition, but it will help us to learn a lot about the dynamics of the system, about certain phenomenology which applies, which has its correlates in the behavior of the system that we explore, and we will learn certain new concepts. And that's why this is so useful to us at this stage, yes.
But for this explanation, we just ignore the h of k of
For?
the hk0, you say it's small enough or you ignore it?
No, I do not have to ignore the hk of 0, because there is nothing symmetry or asymmetry.
No, but for changing the energy to be negative?
No, I did not. No, my h of k includes this and this. You see, this, what I demand to be negative is this whole term. This whole term should be negative. And I have the same thing here. I only wrote it in... I omitted this step, writing this plus hk0 here. But this plus hk0 is hk, the total thing. So this is what I wanted to show you. And now we go to the real truth. Not the real thing yet. The real thing is biology, but the network. Until now, we mainly here, we already started to talk about something which is more than a single element, but we look at what happens to a single element. But now I want to look at the dynamics of the entire network. And then we have to mind that there are many possibilities here, and let me just briefly tell you what are the different possibilities, the different lines of approach, and we shall immediately adopt one of them and stick to it. See, when you have a number of point neurons, this schematic map where you have these point neurons, then network depends, the hardware of the network depends on a number of things. First is the physical structure, and that is the anatomy. That is how many neurons there are, and who is connected to whom. We could have them all connected to everybody. We could have sparse connections, that one to a few or one to many. We could have certain structures, and the other thing, of course, that determines is the hardware impressed upon the synaptic junctions, the JIJ. And now let's see what are the extreme possibilities. We could have a network, for example, where we have N1 neurons in one group, and then N2 neurons in another group, and so on. And the dynamics of such a network would proceed as follows. There would be an input group, and that input group receives signals, initial signals, and then every neuron in this group is connected to all or some of the neurons in the second group. And we already know what the dynamics, how every neuron here will change either noisy dynamics or not, will change with temperature, and then it will proceed as that, and such networks we refer to them as layered networks, although they do not, the neurons do not have to be literally in one layer, but it is a group, and neurons from one group are connected to neurons from the second group. There are no connections within the group, and such networks, in such a network, we will have a certain configuration. Let me denote it by 1. It's S1, S1, S2, Sn1 at time t, and at time t plus 1 we shall look at the configuration here, and we shall look at the configuration there, and there will be an input layer, an output layer, and such networks relate a certain input to a certain output, which we have to read out. Such networks are very common in theories, models of learning. We shall refer to that, but they are not the main thrust of neural networks 1. They are abundant in neural networks 2, in more advanced, which focuses more on learning. Then the other extreme would be a network where there is a lot of feedback, and there are many such connections. What
about auto connections?
Oh, no. Sorry, I should have said that. JII in our models is zero. There's no autoexcitation. And such connections, and in the extreme case, of course, we could have everything connected to everything else. And you note that when I do, there are two connections between this neuron and this neuron, because in principle they are unidirectional, these connections. If we ignore that asymmetry and assume that everything is symmetric, then there is only one connection between two neurons. Yeah? So that we can also have. And now we could have sparsely connected networks, that every neuron will have random randomly randomly connected to a certain fraction of all the other units. And still, this will be a network with a lot of feedback. What we shall do in this course, we shall mainly explore the dynamics of these kinds of networks. And that's what we start doing now. And see what we So if we still stick to this time scale of discrete time intervals, then at a certain time t, the network is fully characterized by the state of all possible elements. So it is a vector, a collection of n bits of 0 and 1. This is a possible. So let's say that I, we can say a certain collection of S at times t. This is what determines, by the curly brackets I denoted as specific configuration. This is what determines, this what describes, defines the network. Now, if we adopt, and that's what we shall do throughout almost everything that we'll do, we adopt this model where there is noise, temperature, or the metaphor of temperature, then we do not know what is, we cannot know with certainty, even if we follow the dynamics, we cannot know with certainty what is the configuration or the state of the network at a given time t. We can only talk about probabilities. We can say that P I and t is the probability of having configuration I or state I of the network at time t. Suppose we now we look at the dynamics of the network, and we want to see what is the state of the network at times t plus 1. So first of all, we do not know exactly what was the state of the network at time t. We have only a probability. And then, suppose that the network was in state I, then the transition to state j also occurs. We can talk about only in probabilistic terms. So if I want to ask what is the probability of the network, the probability of having state I at time t plus 1, what I have to do, I have to sum over all possibilities at previous time, namely over all possible configurations j at previous time, and then multiply that by the probability, which I denote by big W, of going from j to I, and summing over it. Yeah. Now this W is here, I mean,
by I, the state of the
network.
You mean for each neuron specifically?
No, for the whole network.
Okay, binary vector. Any binary vector that would represent the activation.
Binary, there are 2 to the n states, where capital N is the number of neurons. There are 2 to the n possible states. And therefore, in general, Wij, which is a matrix, it connects term configuration J with configuration I, is a matrix of 2 to the n, rank 2 to the n times 2 to the n. And we'll have to make certain assumptions about this W, because you can have a number of possibilities. You can assume that at time t plus 1, every neuron in the system looks at its field and decides whether to flip or not. And this we would call parallel dynamics or synchronous dynamics. Usually this is not the case. To take small t, this will not be the case. The other extreme is what we call asynchronous dynamics, or something which is more descriptive. A better description is Ssf Dynamics, which means single spin flip dynamics, where at every transition only one of the spins taken at random, one of the spins will decide whether to flip or not. If our delta t's are not too big, if they are too big, then in that time interval, many or all of them will do something, or not do, but undergo this. But if delta t is sufficiently small, you pick one of these, and therefore our Wij will be a matrix which has in every row will have how many? In every row.
N elements would be...
But no, they are different. We'll have one, because every row connects you with a configuration I to how many? To n? To n. So there will be, so it will be a very sparse matrix, because it's 2 to the n times 2 to the n. Most of it is 0. We shall write that explicitly in a minute. We shall adopt this kind of dynamics and see where that can take, where this will take us, and what we'll learn from our networks. Now let us explore this a little. Of course, Wij is also a probability. All the p's are probabilities, and therefore p summed over all i's has to be 0. Has to be 1. They are positive numbers that sum to 1. The same applies to Wij, because if you are in state J, then you have to go somewhere or stay there. And therefore, if you sum I, this over all i's is 1. So let us now look at this and rewrite it And if we, in the following way, that we write this j not equal to 1, w. Huh? Yes, Sheila, what's the question?
I don't understand why that is 1. It's not supposed to be on all i's and all j's.
No, because you are at certain, this assumes that you are now at configuration J.
And a certain j.
You are configuration J, and from there you have to go somewhere, or stay there. Therefore, summing over all I gives you 1, and this will write as plus W sorry, W J, this has to be J not equal to I, and this is a sum over J equal to, this is I, P I, P, J, T. What? Now, it says here a sum over J, and I take the particular value of one moment. It has to be
T of I, T I.
J minus I. Here I have it minus I, and I will be no. This is the way I want it, because I take J. I sum here over J. So this is the term where J equals to I. Here I excluded the term J equals to I. Here I include the term J, and now I will use this.
So the left element should be PIC. The left element right will be to the right?
That's, you are right. That you're right, yes. And this, I write as 1 minus sum over J over sum over J not equals to I, W J and let me take this last step here, and then we interpret what we got. We have pi P I T plus 1 minus, you see here I have 1 times Pi of t minus Pi of t. And this was J not equal to I, W I J P J of t minus W J I P I of t. Now you see, this is very easy to interpret this term, because this tells you, the left-hand side here tells you by how much the probability of configuration I, by how much the probability of configuration I has changed, or let us say increased. So this is equal to balance of two terms. One is the probability that increases, this probability increases due to the fact that at time t we had configuration J, and from all those configurations we got into configuration I. And it decreases, here is the minus side, for all the elements, because all the processes were in the past, in the previous time, we were already in configuration I, but we left it to all other configurations. So you see, it makes sense. What we have here is, suppose we of course can transform it into a differential equation, because what you have here, you see, we can define certain transition rate, which we can always define if the transition probability will go to 0 as we decrease the time interval. There's not enough time to make the transition. On the other hand, the transition rate remains constant as we reduce delta t. That is the definition of a derivative. So if we divide everything by a delta t, we'll have here p of I t of I at time t, and then we have j I. Let me write it. Denote the rate by a small w, p j of t minus w j I p I of t. And you see that this condition j different from I don't have to write it anymore, because if j is equal to I, then the two terms here cancel. So so let me drop this. We have sum over j. And I, so I make a remark, we break now these w's, whereas these were normalized in the sense.
Just a sum over 1.
Oh, sorry. I sum over 1, not over I. Thank you. I sum over j, but there is no condition different from I, over all j. The other thing which I can tell you, in a nut, just that the w's were probabilities, and therefore sum over all w's